Alright, here we're up to 7.1 and we're going to discuss about sets and subsets for the 214 part of this course. And some of you may have even seen sets or have learned about sets before, and hopefully maybe this will be somewhat of a review. For others of you, this may be new and unfamiliar, so we'll try our best to try to make this as clear as possible. So, we want to ask ourselves, what are sets? Well, set theory, sets come from a branch of mathematics called set theory. And this is a branch of mathematics that uses sets as its foundation. It can be seen for some mathematicians as a foundation of all mathematics, since numbers can be thought of as sets of objects. It is also the foundation of how we think as humans and tend to categorize things even at a very young age. So now we're going to introduce what's called set theory notation. So each of these definitions we're going to discuss more deeply as we go along in this session. So here we go. A set is a collection of objects. The universal set is all the objects that are under consideration, meaning all the objects that are there. We use curly brackets to put around the list of elements that are in the set that we are discussing. And we can either use words or symbols or whatever we want to put inside these brackets to discuss or describe what is in our set. This symbol means is an element of, and it kind of looks like an E. And that means that it is a part of that set or a member of that set. And then if we draw a line through that, it means that it is not an element of that set. This symbol means a subset. So it can either mean something that is a part of the set, meaning inside of our original set, or it can be the entire set itself. Because it has an equal sign, there's that equal sign, just like when we talk about greater than or less than, and we have greater than and equal to and less than or equal to, it could also be the entire set itself. So it turns out that a set is a subset of itself when we use this particular symbol with the little line underneath. And a subset would be any of the members of a set that is there. This means, when we put a line through it like that, this means it is not a subset. So in this case, we don't even use the equal sign underneath because it's assumed that it's not a subset. Now, as mentioned, we use curly brackets with nothing in it to discuss a set. But if the curly brackets have nothing in it, that means that it is the null set. Now, another symbol for null set or empty set is this symbol. You do not want to put a symbol or anything inside of that if you put the curly brackets. It's either you write this or this, not together. A with a little tick over here is called the complement. It can also have a little C, but here we just have the tick. And that means all the elements that are not in our set A. A with a little upside down U means the intersection of sets. So that means that the elements in A and in B where the two sets overlap. And then finally, where A union B, that means the elements in A or B, which means of all of the elements of both these sets. So we can make sets out of all kinds of objects, even a little guy over here. But what we're going to do is we're going to look at the set of yellow objects inside the curly brackets here. So we have a triangle, a circle, and a rectangle. So that would be a set. These are objects. We can put whatever we want. We can put a cat, a dog, and a rat if we want to. But here we did the set of yellow objects. We can also put numbers. Now remember, we talked about the natural numbers a little bit earlier in our last section, and remember, I wrote it out as a set, and I even began to discuss sets, and I put, remember, the set of natural numbers in curly brackets, and I put 1, 2, 3, 4, and there should be 3 dots, which means goes on forever, and then I close it with a curly bracket. Now let's look at example number 7a, and it asks us, how would we write that a yellow triangle is an element of the set of yellow objects? Well, that means that we would have the yellow triangle and use that symbol, meaning element of, and then we put the curly brackets with our original set, because we see that indeed there is a yellow triangle in there, and that means that it's an element of it. So this says the triangle is an element of the set of yellow objects. So now we want to ask ourselves, how would we write that 3 is an element of the set of natural numbers? Well, we can write, we see that 3 indeed is in here because that's a natural number. And even if we had 7, 8, 9, they're also in here too. We just don't write them all out because this will take forever to write all the natural numbers. So we just wrote a few. So what we do is we want to write 3. 3 is an element of 1, 2, 3, 4, or however many numbers we want, and then dot, dot, dot. And in words, what this is 3 is an element of the natural numbers. But we have to add, what about -3 with respect to the counting numbers or the natural numbers? Well, we see that we know from our earlier chapter that -3 is an integer. It is not a natural number. So what we have to do is we have to use that other symbol that we had, and we write -3 is not an element of 1, 2, 3, 4, etc. And in words, -3 is not an element of the counting numbers or natural numbers. Now, as I told you also in an earlier section, I told you that the natural numbers, this is the symbol for the natural numbers or the counting numbers, the N with a little double bar over here. So we can also write, instead of writing out that list, we can write 3 is an element of N and -3 is not an element of N using those symbols. Now there's a type of notation that we use that I've mentioned earlier too, is there's a thing called set builder notation. And this is a way to describe the set without listing all the elements. So what we do is that instead of listing the elements in words or symbols, we use this particular notation. When we do list elements, we call it the roster notation. And we use curly brackets to indicate a set as usual. And when we do this, when we use the set builder notation, as I said, we're going to use curly brackets, and we begin with a variable to show that the element in the set is going to behave according to the rule that we're going to right after the line. So, for example, the line. So we begin with x, our variable, and here is the line, and then after this is going to be our rule. And this line means this is read as the set of all x such that, which is the mathematical way of saying that the rule, the rule we're about to state, will follow that line. And then we write the rule in words or symbols and end the whole thing by closing it with one of these curly brackets. So let's look at question number 2. So we're going to describe this set using the set builder notation. Well, we see that we're starting at 5, 6, 7, 8. So this looks like it's the set of natural numbers that starts at 5. So there are two ways we can do it. We can write it as x, the set of numbers such that x is greater than 4, because it will not include 4, and x is an element of the natural numbers, so that means we know because of the natural numbers that it'll start at 5. Or we can say that the set of all x here, such that x is greater than or equal to 5, meaning that we're going to start at 5, and again, x is an element of the natural numbers. So here we see that it's going to go on and on forever, so we can just write greater than or equal to in this case. But let's say it's finite, and we only have 3, 4, 5, 6, and 7. Well, that means we have the set of all x such that we start that x is between. It can be between, meaning that here we have x is greater than 2, which means that it starts at 3, and x is less than 7. And of course, that's one way we can write it, where x is an element of the natural numbers. So x is between these. X is not all the natural numbers, it's only a few of them. Or we can write the set of all x such that 3, because we start at 3, is greater than or equal to x, because we're starting at 3, so it'll include 3. And where x is in the middle, and then it's between greater than or equal to 6, where x is an element of the natural numbers. All right, let's look at question number 4. And we're going to try to describe each of the following sets using our symbols, and I'll just say it in words. So here we have the set of elements, and we have the natural numbers from 7, 8, 9, 10, and it goes on and on and on. So it's a set of natural numbers from 7 on. For B, we have only a finite number of natural numbers. So it's only the set of natural numbers 10, 11, and 12. For C, we have, similarly for C, we have the set of natural numbers 1, 2, 3, 4, and 5. And these are elements of the natural numbers. But in D, we have something slightly different here, because if we go on and on forever in the negative numbers, we're not just going to have the natural numbers, we'll start including the whole numbers and the integers. So this means that the set of all integers from 5 to negative infinity. So how do we express all of this using the set builder notation? Well, let's look at A. Well, in A, there are two ways we can actually express this. One way, we can include 7, and the other way, we can say that 6 is greater than 7, but doesn't include 6. So the way we can write that is the set of all x such that x is greater than or equal to 7, and x is an element of the natural numbers. So when it's greater than or equal to 7, it'll include all the numbers from to a positive infinity, so this will go on and on and on and on forever. Or we can say x is greater than 6, where x is an element of the natural numbers, where greater than, since it doesn't have an equal sign, will not include 6, and since it's the natural numbers, it'll automatically assume that it's the next number 7. Now let's look at a situation B where we only have a finite number of numbers. So here we have to make a sandwich where the set of all x such that x is between and inclusive. In this case, we're going to include 10. 10 is x is greater than or equal to 10, which means it includes 10, but x is less than or equal to 12, which includes 12, but also in the middle, 11 in this case. Or we can write it, because it is the natural numbers, we can write it where the set of all x such that x is greater than 9, which means it doesn't include 9, so it jumps right up to 10, and x is less than 13, which means it doesn't include 13, which means it just goes to 12, where x is an element of the natural numbers. Well, how about this next one? Well, we can't write it this other way. We can only write it this way, where the set of all x such that x is greater than or equal to 1, because the natural numbers only start at 1, and then we end it at 5, where x is less than or equal to 5. And x is an element of the natural numbers. But we can't write 0, okay, is less than x, because 0 is not a natural number. So we cannot write it this other way, because 0 is not part of the natural numbers. As mentioned earlier, this is becoming part of another number system. It's no longer just a part of the natural numbers, because as we get smaller and smaller, we'll not only get 0, the whole numbers, but we'll also start going into the negative numbers to negative infinity. So this means that the set of all x such that x is less than or equal to 5, meaning that we're ending it here at 5, and x is an element of the integers. Since, as we discussed earlier, the integers include both the natural numbers and the whole numbers. And in this case, we can include that 6, because 6 is an element of the integers, so we can say x is less than 6, which means that we're starting this going smaller and smaller, starting at 5. All right, let's look at the subset. All right, so we're going to look at this particular symbol, and this means is a subset of. So A is a subset of B if every element of A is contained in B. And that's why what we write is, we would write A is inclusive in B, or is a subset of B. So for example, in number 5, this is the set of smiley emojis. Is it a subset of the set of silly emojis? So let's look at these emojis. So here are the smiley emojis, and here are the silly emojis. So yes, we can say, indeed, it is a subset because all these smiley emojis, so we have this one here, there it is, and we have the one with the freckles here, and there it is, and then we have this one, there it is. So all of these emojis are in this set. So they're inside our original set, or the bigger set. So is the set of alarm emojis a subset of the silly emojis? Well, let's see. Here's the alarm emojis. Do we see the double exclamation point here? No, we do not. Yes, we do see this guy here, but we do not see the alarm clock, nor do we see this exclamation point. So therefore, since this one, and this one are not in the original set, which is this bigger set, we can conclude that no, it is not a subset of the alarm emojis are not a subset of the silly emojis. Because the alarm emojis are not in here. In question number 7, let's look at it. So we have let A is equal to 4, 5, and 6, and we have set B, 1, 2, 3, 4, 5, 6, and 7, and then we have set C, 6, 7, 8, and 9. So we want to ask ourselves the question, which of the following is true? So, is A a subset of B? Well, let's look at A. We have 4, 5, and 6 in A, and B, 1, 2, 3, 4, 5, 6, and 7. Well, let's look. 4, well, that's in B. 5, that's in B. 6, so that's in B. So we can conclude that indeed A is a subset of B. How about A, a subset of C? Well, let's look at A. Well, 4 does not look like it's in C. 5 is not in C. 6 is in C, but since 4 and 5 are not a subset of C, we can conclude that indeed A is not a subset of C. And how about this last one? Is C a subset of B? Well, let's look. 6 is in B. 7 is in B. Uh-oh! 8 is not in B, and 9 is not in B. Therefore, C cannot be a subset of B. So we conclude that it is true for the first one, but it is not true for the second one, nor is it true for the third one. So therefore, the only one that's true is A is a subset of B, and the others are not true. In question 8a, is the subset of all dogs is the set of all dogs a subset of the set of all animals, or the other way around? Well, we know dogs are animals and all dogs are animals, but a cat is not a dog. So therefore, all animals are not dogs. So we can conclude that that all dogs are a subset of all animals, but not vice versa. So that we conclude. So here it is. We can write dogs are a subset of animals. How about, is the set of all multiples of 2 a subset of the set of all multiples of 4, or is the set of all multiples of 4 a subset of all multiples of 2? Well, let's look at it. So let's look. We see the multiples of 4, and let's look at the multiples of 2. So here are the multiples of 4. So it can go less, smaller, and smaller, and smaller. 4, 8, 12, and bigger, and bigger, and bigger. And we see this one is 2, 4, 6, 8. This gets smaller and smaller, bigger and bigger. And indeed, we would have 4 in here. 8 would be in here. So it turns out that the multiples of 4 is indeed a subset of the multiples of 2. So we can write that the multiples of 4, and we're just writing it as a set, and that it is a subset of the multiples of 2. In question 9, we're asked, is the set of all green dogs a subset of all dogs? Well, in nature, as far as we know, yes, because in nature there are no green dogs. But the empty set is a subset of all dogs. So we write that the empty set, which we can put as this, or, and remember, or, a set with nothing in it is a subset where X such that X is a dog. So the empty set is a subset of any set. So the empty set or the null set is always a subset of our original set. In question number 10, we are going to look back at our yellow shapes and see that is it a subset of itself? Yes, because according to our definition, the entire set can be a subset of itself because we have that equal sign. And that means that a subset with the symbol like this is similar to a less than and equal symbol, so that means that one that is equal to the other can be a subset of this. So this just like we did before, so we can have, yes, 5 is less than or equal to 7 is true, but also 5 is less than or equal to 5 is true because of that equality. In question 11, we're going to look at how many subsets does this set have. So here we have this set and we have a star in it. So we see we've already learned that the null set or the empty set is a subset of any subset, of any set, and the entire set itself is a subset of the original set. So therefore, we have the empty set and the set with the star in it, so therefore we actually have two subsets. So we have the null set or the empty set, which is always a subset of a set, and we have the entire set itself, which is also considered a subset. So therefore, there are exactly two subsets. Let's look at now example number 12. We want to know what about a two-element set? How many subsets does it have? How many subsets will be contained in the set CD? So let's look at the set CD. We've already said that CD, the null set or the empty set, is a subset of CD. Well, we know that C is a subset of CD because C is in there. We know that D is a subset of CD, and then indeed CD is a subset of itself. So any two elements set has exactly 4 subsets. Let's go a little bit further to now one where we have 3 elements. So let's say we define our 3 elements as X, Y, and Z. So we want to figure out what are its subsets. Well, first we start out with the null set, because we've already said that the null or empty set is a subset. So that's 1. Then we want to look at the single elements in this set. So we have X is a subset of X, Y, and Z. We have Y is a subset of X, Y, and Z. And then, of course, Z is a subset of X, Y, and Z. Now we go on to the 2-element combinations. So we have X and Y is a subset of X, Y, and Z. X and Z are a subset of X, Y, and Z. And then Y and Z is a subset of X, Y, and Z. Now you may ask, so there, oh, and of course, it's a subset of itself. So X, Y, and Z is also a subset. So any 3-element set has exactly 8 subsets. Now you may ask, well, what about YZ? Well, YZ is the same thing as ZY. We don't consider this separate because the elements are the same, not how they're positioned in the set. So it doesn't matter what order we put it in. What matters is the elements are themselves. So the order we put it in does not make any difference. So now we want to see what pattern we can see in the number of subsets. So we look at what we've done. Well, we find that if there are no elements in a set, we have one subset, which is the null set. And then we found that in example number 11, if we have one element, meaning the star, for example, that means we have 2 subsets, the null set and the set itself. And then we found in example number 12 that if we have 2 elements, say A and B, we found we got 4 subsets. And then in example 13, which had 3 elements, we found that we had 8 subsets. Now we're going to see, looking at these patterns, so we're looking at the pattern here, and we want to see if we can deduce the number of subsets a 4-element set will have. So we're asked in question number 14 to look at this pattern and to think, how many elements do we think a 4-element set will have? And then we're going to finally write a formula using n to show the number of subsets. So we see that the number of subsets doubles in each row. And since it doubles in each row, that means a 4-element set will have 16 subsets. So we can figure this out using the formula for the number of subsets is 2 to the n, where this means the doubling, the 2 here at the base is the doubling, and n is the number of elements in the set. So for a set with 3 elements, 2 to the n, where n is equal to 3, would be 2 to the third, which would be 8 subsets, and this would correspond to our example 13. So then we can guess, finally, that a 4-element subset would be 2 to the fourth, and 2 to the fourth would be 16 subsets. In question number 15, we have this set with 3, 4, 5, 6, 7, and 8. And we want to figure out how many subsets does this have. So we're going to count the number of elements. We have 1 element, 2 elements, 3 elements, 4 elements, 5 elements, 6 elements. So that means that n will be equal to 6. So we would take 2 to the 6th power, and that will give us 64. So therefore, this particular set, we will have 64 subsets. Isn't that a lot easier than writing them all out separately? So here we have the set with 6 elements in it. We use our formula, and we find that 2 to the 6th power is equal to 64. So it has 64 subsets. Well, thank you very much, and stay well, and until the next video, bye.